December 1944, Ardennes, Belgium. General Alfred Jodl noted in his diary that the American artillery had weakened at last. In the German trenches, the breakthrough was believed to be near, the final counter-offensive, the Wehrmacht's masterstroke. But then, without warning, shells began to fall that did not hit the ground. They exploded in the air, a few meters from the soldiers' heads, as if they guessed the exact moment to kill. This illusion of advantage, so carefully constructed by the German High Command, was about to be disintegrated, not by a tank, not by a bomb, but by a tube the size of a finger hidden inside a projectile. A little circuit that I was thinking, and that he chose when to explode. In this documentary, it will be revealed how an invisible weapon, unknown to most, quietly defined the outcome of dozens of battles. A device that turned trenches into booby traps, planes into easy targets, and bombings into math. A weapon that the Germans found, studied, and dismissed it as impossible. They didn't believe what they saw, and that's exactly why they lost. But before we dive into the data, there's one statistic that defines this story better than any speech. During the Battle of the Bulge, in just 3 minutes, 702 German soldiers were killed by explosions that came from the sky, without a single direct shot having been fired. A conventional projectile needed up to 2,000 rounds to bring down a single plane. With the proximity fuse, 155 was enough. In the London defence, 79% of the V-1 bombs were shot down before touching the ground. Not by miracle, but by calculation. The most effective weapon of war was also one of the least visible. If you value historical accuracy, the memory of detail, and the engineering that shaped the century, please consider supporting this work with a like and your submission. This helps us to continue revealing how logic has won over force. In 1939, as Europe plunged into yet another war, a small group of British scientists sketched out what looked like a piece of science fiction, a projectile that would detect the enemy in the air and explode at just the right moment, without touching the target. It was the idea of a brain inside the ammunition, a device that would eliminate the randomness of artillery and turn every shot into lethal mathematics. The concept was technically clear, but physically inconceivable. The challenge was cruel. How to build a miniature radar embedded inside a projectile the size of a thermos, capable of withstanding an acceleration of up to 20,000 times gravity during firing. Ordinary radio tubes broke only when the hand fell out. A projectile launched from a naval gun subjected each internal component to forces equivalent to a high-velocity impact. Even the most optimistic engineers considered the idea suicidal. The British Air Ministry recognized the potential of the concept, but it also recognized something even more definitive. They simply did not have the means to develop it. There was a lack of resources, factories, materials, and above all, time. The United Kingdom was fighting for its survival against a Luftwaffe that seemed endless, and it was then that in an almost desperate gesture the British did something unprecedented, and, as history would show, with no return. They gave away their biggest secret. The TISAD mission was the first act of irreversible trust between two powers. Sent to the United States in September 1940, it carried the most advanced in the British arsenal, from the magnetron, which would revolutionize radar, to the first concepts of proximity fuses. It was a technical and moral pact. Britain trusted that the Americans could turn ideas into weapons, and fast. The Germans, on the other hand, were trapped in a structure where science was seen as subservient to power. Research existed, but it was fragmented by internal rivalries between armies, navies, and parties. Bureaucracy suffocated the engineer. In the United States, the scenario was different. The Roosevelt administration, driven by a combination of pragmatism and urgency, gave carte blanche to its physicists. It was the America of unlimited production and unprecedented collaboration. where the idea of a thinking tube wasn't just possible, it was a national goal. The National Defense Research Committee, NDRC, has been tasked with bringing together the best brains in the country. Among them, one name would stand out: Merle Tuve, a physicist at the Carnegie Institution, an expert in electronics and waves. Tuve looked at the British concept and saw no impossibility. It saw an engineering problem, and like every engineering problem, it would be solved with precision, time, and resources. His laboratory began to work day and night. The statistics of this race are ignored to this day by popular history books, but they say it all. In just 18 months, the United States tested, improved, and began producing the first viable proximity fuses. A cycle of innovation that would have taken years in peacetime has been compressed into weeks. For comparison, Germany spent 3 years just trying to standardize a reliable radio tube for its portable radios. And here it is, worth pausing for a fact ignored by German intelligence. While Berlin produced about 3,000 electronic tubes per month, the United States produced 2 million per day. Yes, per day. If this number surprised you, write in the comments, "Logistics wins," because that's exactly what happened. But the real American miracle was not just in the quantity, it was in the quality of the coordination. Tuve worked with scientists, military personnel, factory engineers, factory workers, and even housewives recruited to assemble parts under microscopes. Each tube had to be resistant to impact, vibration, and heat. Acceleration tests were done on hydraulic platforms created from scratch. Entire teams were assigned only to monitor microscopic flaws in the seal. The standard of demand was so high that later NASA would use the same protocols in the first satellites. The production of the proximity fuse became the largest electronic miniaturization effort ever recorded up to that point, all inside steel housings which would explode before any reuse. It was, in short, a disposable computer. In 1941, the first functional unit was tested, and it worked. A tiny radio tube detected an aircraft, activated the circuit, and detonated the projectile 10 meters from the target. The gun thought, and he won. Meanwhile, on the other side of the Atlantic, the Germans laughed at the possibility. His technical command classified as absurd the idea of a radar coupled to a grenade. Intelligence documents show that the hypothesis was considered statistically unlikely. To them, Americans' electronic complexity was seen as excessive, inefficient, almost childish. What they didn't understand was that when the goal is to destroy a plane with a single shot, no effort is excessive. This technical arrogance would cost thousands of lives, and it would set the stage for a tactical collapse on several fronts. Because while Germany believed that it would win by superiority of doctrine, the United States was building the doctrine of the future, one where it no longer shoots at the enemy. It explodes before it is seen. But all of this was just the beginning. The first test in combat had not yet taken place, and when it did, it completely transformed the Pacific Ocean and naval warfare itself. What happened that day would force the Japanese to create a new tactic of desperation, and the Americans, recognizing that they had crossed a point of no return. Washington, September 1940. While the United States had not yet declared war, a group of British scientists quietly landed on American soil with a mission that carried more weight than any warship: to convince the Americans to accelerate the future. It was the Tizard mission. Named after physicist Henry Tizard, it didn't bring tanks, soldiers, or gold. It brought patents, prototypes, and technical notebooks with the most advanced secrets of British military science. Among them, cavity radar, jet concepts, bomb designs, and discreetly wrapped in a brown paper tube, the embryo of an idea that seemed absurd to the world, but essential for those who had already faced the burning skies: the proximity fuse. For the British, the proposal was simple and desperate. We had the idea. You have the means. Make it work. It was a gesture of strategic humility, unthinkable in authoritarian regimes, and it was this voluntary surrender of knowledge that initiated one of the greatest technological leaps ever made in wartime. In Germany, such a transfer would be seen as weakness. In the United States, it was understood as an alliance. The reception of the mission, however, was not protocol. The Roosevelt administration, already aware of the global escalation, had secretly created the National Defense Research Committee, and the scientist Vannevar Bush, its director, immediately understood the value of the British cargo. The cavity radar would become the backbone of anti-aircraft defenses, but it was the concept of the proximity fuse that attracted particular interest. It was more than an idea of defense. It was a doctrinal rupture. If it worked, it would change everything: the time, space, effectiveness, and cost of each shot. The proposal was given to a man who, until then, was little known outside academic circles: Merle Tuve, experimental, rigorous, pragmatic physicist. Tuve was not a visionary in the classic style. He was a problem solver, and when he read the British notebooks, he didn't laugh, he didn't hesitate, he didn't ask permission. It has just begun. The T-section was born there. Housed within the Carnegie Institution of Washington, Section T was officially a research group. In practice, it was a laboratory of silent war. Its mission: miniaturize, strengthen, automate, building an electronic circuit capable of detecting moving targets, calculating distance in real time, and activating a detonation at the exact moment. All this without fail, and within a projectile launched at more than 1,000 kilometers per hour. It was a bigger challenge than the Manhattan Project itself in terms of immediate technical feasibility. But there was a difference. While the atomic design was still theoretical in 1940, the proximity fuse already had clear application, direct demand, and the potential for immediate use. Tuve organized his team with an almost military precision. Theoretical physicists, radio engineers, instrumentation technicians, and skilled workers worked side by side in continuous shifts. Every test tube, every capacitor, every weld was recorded, analyzed, and tested to exhaustion. Time was the real enemy, and the pressure was moral. Meanwhile, the Germans were taking the opposite path. Science was subject to politics. Heisenberg and other elite physicists operated under surveillance, and non-aligned ideas were suppressed by doctrine. The Luftwaffe maintained its own laboratories, the Kriegsmarine others, and the army was still trying to protect its internal patents. Each arm of the war effort competed with the others. There was no functional centralization, nor a spirit of collaboration. Germany's best minds were isolated or silent. And at the moment when the Tizard mission opened doors between nations, the Reich closed the windows of science. Tuve quickly understood that the task was not just technical, it was industrial. And at that point, America had an invisible weapon: the ability to climb. Instead of striving for perfection in the first model, the T-section sought minimum reliability with maximum output. The first prototypes failed, yes, but each failure was documented, redesigned, and improved. In less than 18 months, tests with live projectiles showed hits that seemed like magic. A howitzer exploded 10 meters from a moving target without any mechanical detonation. A marine projectile brought down a plane before the onboard radar detected its approach. And all this was done with vacuum tubes the size of a finger, welded by workers in ammunition factories that, months before, produced domestic flashlights. It was the birth of electronic warfare at scale. The effort extended to a national production network. Factories in Baltimore, New Jersey, and Illinois were retrofitted to mount the new fuses. Each day, thousands of units rolled off the lines. The data were clear. In 1942, more proximity fuses were already being produced than artillery pieces. The production was not an answer, it was anticipation. The United States was preparing an invisible, silent, and completely lethal arsenal. And the Germans, even with espionage reports pointing to strange circuits in the captured warheads, maintained the same opinion. Impossible. An officer of the German Technical High Command wrote in January 1943, "The Americans are using induction-based blasting systems, but that kind of accuracy is still shaky. It's probably a technical bluff." It was not a bluff, it was the T-section silent. But the decisive moment was yet to come. It's one thing to test in the lab. It is quite another to operate under real fire. The first combat in which the proximity fuse was used would reveal more than the effectiveness of the weapon. It would reveal that the war had entered a new stage, and that the enemy, even seeing the threat with his own eyes, would still not be able to understand what was happening, because the gun thought. And now he was thinking about killing. Inside the austere building of the Carnegie Institution, without flags, without uniforms, without fanfare, one of the quietest and most decisive battles of World War II was taking place. Merle Tuve, a physicist with a clinical look and a restrained voice, commanded a group of civilian scientists who worked as if every second cost a life, because in fact, it did. The pressure was not just technical, it was existential. On the other side of the world, kamikaze pilots dived on American aircraft carriers, Japanese submarines sank convoys in the Pacific, and reports of losses arrived at funeral pace. Between experiments and calculations, the engineers of the T-section read the war teletypes with moist eyes. One technician wrote in his diary, "We lost more men this week. Maybe if our circuit had worked before." The weight of responsibility was invisible, but absolute. It wasn't just about building a weapon, it was about preventing the war from continuing in the dark. Each tube, each welding wire, was assembled under the awareness that a technical failure would not be measured in centimeters, but in coffins. The main problem was brutally simple: physics. An artillery shell, when fired, undergoes an acceleration of up to 20,000 times gravity. This means that any electronic circuitry within it needed to be not only functional, but almost indestructible. At the time, common vacuum tubes burst with the impact of a fall on the countertop. To survive the shot, it was necessary to reinvent the very concept of miniaturization. The plates needed to be sealed with microscopic precision, the components welded with specific alloys to resist heat and vibration, and the radar needed to operate with stability in milliseconds, in mid-flight, and in a combat environment. Every technical detail was an obstacle that in normal times would take years of research. Merle Tuve was months old. The solution came from the unprecedented collaboration between science and industry. Civilian companies such as Raytheon, General Electric, and Western Electric were instructed to adapt assembly lines to unprecedented standards. Housewives were trained to assemble circuits under microscopes. Retired soldiers returned to teach ballistics, and engineers from Bell Labs created new types of tubes exclusively for the project. The war on science was, in practice, a national effort. And even then, failure was routine. More than 80% of the first prototypes failed tests, but they failed better. With each mistake, the team learned something new, and he continued. Because every hour without this weapon cost more than time. It cost strategic initiative. Meanwhile, on the other side of the ocean, Germany followed a different logic. Its scientists were isolated in parallel programs, supervised by officers with no technical training. Priority was given to prestige projects, rockets, revenge weapons, oversized tanks. The concept of the proximity fuse was not even clearly understood. German doctrine still believed that power would come from volume of fire and armored mobility. The idea of a smart projectile was seen as too experimental, too unstable, too American, an irony that would only become clear when it was too late. In Washington, the advance was approaching a turning point. By mid-1942, the first functional batches were ready. The final tests involved actual firing at simulated targets, balloons, drones, moving structures. The result was so accurate that one observer declared, "It's no longer a shot, it's an electronic decision." The ammunition now chose where to explode. The psychological impact was immediate among the military who watched the demonstrations. The U.S. Navy demanded full priority in production. The Air Force has initiated test protocols for anti-aircraft artillery, and the engineers, for the first time in 2 years, slept quietly. But the peace was short-lived, because the war did not wait. On Guadalcanal, American forces faced daily air attacks and were unable to maintain control of the naval perimeter. Ship losses were growing. It was time to take the project to the forefront. Merle Tuve himself attended the meeting at which the fuses would be released for combat. It was a risky decision. If one of them was captured, the Germans or Japanese could try to reproduce, or worse, develop countermeasures. But the cost of waiting was greater. The war required risk. And the science was ready. The first shipment of projectiles with proximity fuses left San Francisco heading for the Pacific in absolute silence. Sealed, escorted, catalogued. The sailors who would receive them did not know exactly what they were carrying, but they would soon understand. Because the first real application, a few days later, would have such a devastating effect that combat reports would be classified by weeks. A Navy officer reported, "They started falling before they arrived," as if they knew they were being watched. And the Japanese, without understanding, would return to the radio with a message that would mark the beginning of a new era. Americans have an invisible weapon that kills from the air. The enemy did not yet know how, but I already knew that something had changed, and on the European continent a German scientist would write, that same month, a sentence that today seems prophetic. If they really manage to make this work, the war will be decided by engineers. And they succeeded. The next step was to prove it, not in testing but on the battlefield, and the chosen location would be the Pacific, where the sky until then belonged to the kamikazes. What began as a British theoretical sketch, refined in American laboratories under extreme pressure, became, in less than 12 months, an unprecedented industrial operation. By 1943, the United States was producing more than 70,000 proximity fuses per day. Not per month, per day. Each unit required dozens of electronic components, strict quality control, ballistic testing, and absolute insulation. It was an engineering miracle repeated on a national scale. Factories that once manufactured home radios have been adapted to produce war circuits. Workers without technical training were trained to assemble sensors with millimeter precision. The entire structure of production, transportation, inspection, storage, was redesigned to operate under the rhythm of a global war. It was more than efficiency, it was doctrine. America understood that it was not enough to have a better weapon. It needed to be available in sufficient numbers to change the statistics of the battlefield, and that the Germans simply could not do. Reich Industrie, already depleted by Allied bombing and internal conflicts, struggled to keep basic production lines running. The Luftwaffe relied on parts imported from occupied countries. The army was trying to standardize electrical systems that still used 1938 technology. Meanwhile, the Americans updated their fuses every quarter, with incremental improvements made from combat reports. The feedback chain between the battlefront and the factory worked with an agility that the enemy could never replicate. The irony of this story is that the solution was in front of them. On several occasions, projectiles with proximity fuses were captured by German forces during offensives in North Africa and Italy, but when they opened the devices, German engineers found circuits so miniaturized, so advanced, that they simply refused to believe that it could have been done at scale. A 1944 German technical report classifies the fuses as engineering curiosities, possibly non-replicable prototypes. The conclusion: If these units are really being used en masse, it is an industrial feat that surpasses by orders of magnitude any current Reich capacity. It was not propaganda, it was just true. The German model of development prioritized punctual excellence, unique pieces, precision craftsmanship, a philosophy that worked in peacetime but collapsed under the weight of total war. A Messerschmitt fighter could be remarkably fast, but it took weeks to assemble. The United States, with its standardized assembly lines and industrial integration, was capable of producing 1,500 B-17s per month. War had ceased to be a matter of individual bravery. Now it was arithmetic. And American mathematics was relentless. The budget for the T-section was automatically renewed with each production run. If a piece broke, it was replaced by 1,000. If one assembly line failed, another went into operation. There was no shortage, there was planning. By mid-1944, more than 22 companies were directly or indirectly involved in the production of the fuses, distributed in 10 different states, with intentional redundancy to ensure continuity in the event of sabotage or attack. The thinking weapon had become, paradoxically, the most impersonal of all, produced by hundreds of thousands of hands that would never see the battlefront. But that changed its course with each shot. And this is where the quietest aspect of this victory reveals itself. It was not genius that won, it was execution. The genius can conceive a weapon, but only industry can defeat it. If you're enjoying unraveling these facts and understanding how history has been shaped not just by ideas, but by production and persistence, show your support, like and subscribe. This helps us to continue bringing you detailed and in-depth content about the invisible gears of war. And speaking of invisible gears, there's one number the Germans could never explain, even after the war. Why, in a matter of months, did their V1 hit rates plummet from 60% to less than 20%? The answer was flying in the air, exploding before touching the ground. In the next chapter, we go to the skies of England, where an entire city was saved not by a wall, but by invisible mathematics. And the V1s, which were supposed to double London, fell before they were even heard. January 7th, 1943, Solomon Islands. The light cruiser USS Helena was patrolling the rough waters of the Pacific when the alarm sounded. Japanese planes were approaching in attack formation. The scenario was already known. Dive bombers and fighters that appeared out of nowhere in low descents, aiming at the decks and conning towers with lethal precision. But this time, there was something different. For the first time, the Helena's gunners were armed with a new round of ammunition, visually identical to the previous one, but with a secret inside, the radar proximity fuse. As the enemy planes approached, the 5-inch guns began to fire. The sound was the same, but the effect is not. Before any aircraft could enter strike range, they began to explode in mid-air without being hit directly. There was no visible impact. Only synchronized detonations within a few meters of the targets, as if the shells were waiting for the exact moment to act. Combat reports from that morning described the scene with a mixture of relief, astonishment, and confusion. One veteran sailor wrote, "It was as if God were guiding the shells. They knew." During the attack, 5 Japanese planes were shot down before they even entered the critical zone. There was no need for aim adjustments nor elevation corrections. The internal electronic circuit calculated the distance, reacted in real time, and detonated with mathematical precision. For the first time in the war, a gun thought before it killed. And that changed everything. The psychological impact was immediate. The crews, accustomed to the terror of kamikaze bombings, saw with their own eyes what seemed impossible. A shell that did the job on its own. More than effectiveness, it was autonomy. The enemy was defeated by something he could not see, foresee, or escape. In the after-action, Navy officials classified the result as beyond expectations and requested an urgent doubling of production. The confidence of sailors skyrocketed. For the first time, they had a real defense against the air threat that dominated the Pacific. On the other side, the Japanese noticed something strange. Surviving pilots reported that the American shells seemed to explode in the air for no reason. No maneuver worked. No pattern was detectable. They just fell before completing the dive. Initially, Japanese reports attributed the effects to a new saturation tactic. A more accurate radar was suspected. But no one imagined that the projectile itself had become sensitive to the environment. It was a paradigm shift. The missile, as a modern concept, did not yet exist, but there, over the waters of the Pacific, it had been anticipated, in analog form. In the following weeks, other ships equipped with the new ammunition began to report the same results. In fighting off Guadalcanal, groups of up to 12 planes were repulsed with 50% losses before they completed the attack. The average number of shots needed per kill dropped dramatically, from more than 2,000 to less than 200. And the most impressive thing, in many cases, the pilots did not even know where the explosions were coming from. Psychological fear set in. The Japanese began to suspect that the Americans had developed an invisible field, some kind of flying antenna, or weapons guided by larger ships. The truth was much simpler and much scarier. It was just logic inside the bullet. Meanwhile, in Berlin, the concept was still rejected. The Reich Aviation Ministry had received fragments of American shells with internal circuitry, but the official assessment was that they were experimental devices. A German engineer analyzing one of the fuses wrote, "It is not possible that this is being used on a large scale. If it were, we would be losing aircraft in unacceptable proportions." And indeed they were. They just didn't know why. German technical arrogance, fueled by a doctrine that saw warfare as an elite art, precluded the perception that the battlefield had been automated, that the new war was made of microchips, not brilliant strategies. In the United States, Section T followed up each report with surgical attention. Field data returned to the laboratories, feeding cycles of continuous improvement. A slight delay in the detonation time, adjusted. An excess of false detonations by rain, fixed. The fuse learned. Each version was more accurate, more stable, more deadly. And all of this was produced in industrial volume, with redundancy of supply and complete integration between design and assembly line. It was an ecosystem of war, something the enemies didn't have and couldn't copy. The moment of strategic turning point was consolidating. The American artillery now possessed an efficient, portable, and autonomous air defense. The Navy, previously vulnerable in the open sea, was beginning to regain the initiative. And Japanese planes, once feared for accuracy and fanaticism, now evaporated before diving. The sky was no longer the enemy's territory. Air superiority was beginning to be challenged, not with fighter jets, but with mathematics. Japan, realizing that something was changing, began urgent investigations. But there was no technology, nor time, to understand what had already been in operation for months. The race was no longer for territory, it was out of understanding. And they were too late. In the next chapter, we cross the ocean to Europe. Because while the Pacific saw its skies cleared by logic, London faced a silent threat. A German gun, designed to bend British morale, flew at high speed towards the capital. It was the V1, the flying bombs, and the British were about to discover that the only possible defense would also come from the air, and that, this time, the radar would not only warn, it would explode. June 1944. As Allied forces advanced into Normandy, London faced a silent enemy. On the other side of the Channel, German launch bases were beginning a new phase of the war, automated bombing. They were the V1s, the so-called flying bombs, self-propelled projectiles, launched without a pilot, with only one programmed destination, the heart of England. Every morning, The low, intermittent sound of the engine's pulse heralded the approach of another attack. When the sound ceased, it meant only one thing: imminent impact. In the early days, there was no effective defense. The V-1s flew low, fast, and at constant speed. Too fast for conventional artillery, too slow for interceptor fighters. Fear once again dominated London. The feeling was that once again the city was condemned to watch the destruction in silence. But this time there was a gun. It's a decision. Winston Churchill, pressed by his advisors, was informed that the United States had sent to Britain a restricted shipment of shells equipped with proximity fuses. The technology was too sensitive, too secretive, to be used in areas where it could be captured. Roosevelt himself had urged caution. The risk of the weapon falling intact into enemy hands was considered serious, but London could not wait. And Churchill did not hesitate. In a nightly meeting at the war rooms, he said only, "If this weapon can protect my people, then let it be used now." Authorization granted. In absolute silence, the anti-aircraft batteries around the city were replenished with the new shells. Not a word to the press, no explanation to the troops. Just a new kind of ammunition and one last hope. The change was immediate. In the following weeks, the V-1 kill rate jumped from 17% to a staggering 79%. The bombs were detonated in the air, dozens of meters above the ground, before reaching their impact zones. In many cases, the gunners did not even see the target visually. They just estimated the trajectory, shot off, and the sky exploded. One operator reported it was as if the gun itself had eyes. The feeling among the troops was one of astonishment. The instructions for use were minimal. The shell did all the work on its own. And he did it with a precision that no human could match. The psychological effect was profound. The citizens of London, although still under attack, began to notice that the impacts were diminishing. Sirens sounded frequently, but explosions became rare. The shelters were still full, but the terror subsided. The city resisted, and he survived. The secret weapon had worked, and with it, Churchill's promise that London will not fall gained real contour. What the Luftwaffe had done with strategy and precision in previous years, the V-1s tried to compensate with quantity, but the numbers were against them. For every 100 bombs dropped, almost 80 were shot down. Not by luck, but for science. On the German side, frustration was growing. The engineers who had developed the V-1 believed they were facing an invincible weapon. There was no pilot, there was no human error. The speed was designed to evade most defense systems, but something was happening, and no one knew what. Reports showed that the effectiveness of the attacks plummeted week after week. Some even suggested that the British had created a new type of jamming radar. Others, more superstitious, spoke of dispersion fields or energy shields. The explanation, however, was simple and American. The proximity fuses were doing the job in the absolute silence of their electronic code. No one saw them, but his results were everywhere, in the craters, in the mid-sky. More than technical effectiveness, what was revealed there was the power of a decision. Churchill had authorized the use of a sensitive weapon in his own backyard. British intelligence knew that if a shell was found intact, the Germans would try to reproduce it. But the calculation was moral. London needed to be defended, and if it meant revealing a secret in the eyes of the enemy, so be it. The historical irony is that, even when capturing fragments and burnt circuits, German engineers still thought it was experimental technology in the testing phase. They underestimated not only the weapon, but the political courage that had put it in the field. The Americans, for their part, followed everything closely. The T-section received daily reports from the Royal Artillery on hit rate, operational failures and weather conditions. The information fed a production cycle that did not stop. Each improvement was implemented in future batches. The gun was alive, learned, evolved, and it killed more efficiently every week. The V1 episode marked the first major test of the proximity fuse in civilian territory, and he passed. With this, a new stage of electronic warfare began, because, contrary to what the Germans imagined, this would not be the last application of the technology. She was still far from her climax. The next target would not be a flying bomb. It would be something much bigger, something armored, heavy, insurmountable, and until then considered invulnerable to conventional artillery, because the next battlefield, it would be the ground. December 1944, Ardennes, Belgium. As the German counter-offensive advanced through the snow and silence cut by explosions, a small technical team of the Wehrmacht located, among the rubble of a destroyed American post, fragments of artillery with intact electronic components. It was rare to find this type of preserved material. Rarer still was the one they unknowingly held, one of the best-kept secrets of the Allied war effort, an active proximity fuse extracted from an unexploded grenade. The cylinder contained a complex structure with wax-sealed wires, a small shielded vacuum tube, and an ultra-low frequency transmitter. Engineers examined the piece in silence. After hours, they wrote a technical report that ended with a curiously revealing sentence. This technology exceeds current known production capacities. We concluded that it was an experimental piece or propaganda. It was precisely at this moment that Germany lost the technological war, not because of technical inferiority, but because of ideological blindness. The conviction that an industrialized democracy with civilian-operated factories led by elected generals could not produce something so precise. Nazi technical culture despised American standardization, its pragmatism, its apparent lack of sophistication. The Reich believed in the superiority of artisanal engineering, in individual projects, in revolutionary prototypes. To them, only a genius mind could conceive of such a thing. And since there was no signature, no name, no Nobel Prize behind the piece, they discarded it, literally. The artifact was labeled as non-replicable and archived. The most ironic thing is that in doing so, the Germans had in their hands everything they needed to understand the turning point that was underway. They had the circuit, they had the sensor, they had the vacuum tube. They even had the debris from the antenna. But they didn't have the mindset to accept that they were being outclassed, not by a lone scientist, but by a network of thousands of engineers coordinated by logistics, fed by data, and sustained by an industry that produced weapons like it made cars. And if there was still any doubt about the scale of this operation, it is worth pausing. American production of proximity fuses in 1944 exceeded 22 million units, 22 million. Meanwhile, Germany, battling bombing and copper shortages, could barely produce 3,000 programmable ignition parts a month. If this surprises you, comment, "Logistics wins," because in fact it won. On the battlefront, the effect of this blindness was brutal. With each air attack against American positions, the Germans faced a curtain of fire that they did not need to hit to kill. It was enough to get closer. The troops reported that their planes just crashed without warning. American gunners no longer needed to calculate the exact impact. The gun did it on its own, and he did it without hesitation. When an airplane crossed the fuse's detection zone, it was hit by an explosion that came out of nowhere. Invisible, lethal. And even in the face of mounting evidence, the German High Command insisted on alternative explanations. A January 1945 memo proposes that the Americans were using projectiles with thermal sensors, or possibly some kind of balloon-borne radar. The hypothesis of a radar inside the projectile itself was considered absurd. A Luftwaffe general even wrote that the miniaturization necessary for such a feat will still take years to be achieved. The American response was already in the field for more than a year. This refusal to accept reality was not just technical, it was ideological. The Nazi war machine was based on the conviction of cultural, technological, and moral superiority. To admit that the enemy outdid them in applied science was to recognize that modern warfare was won not only by discipline or bravery, but by circuits, by algorithms, by mass production of intelligence, and this was a war they didn't know how to fight. In the American rear, this war was won every day by female electronics factory workers in Kansas, by engineers in Washington, by logistic officers who coordinated thousands of boxes of ammunition by railroad. It was a collective, impersonal, but devastating effort. A system that, even attacked, continued to work. A war in which each piece had a role, and every piece worked. Because the secret wasn't in the brilliance of the idea, it was in the brutality of the execution. On the field, this brutality translated into tactical advantage. In the Ardennes, in the Philippines, in the skies over Italy, the reports were piling up. The fuses were working. American soldiers were already calling them automatic death. The Germans, in their diaries, began to write down phrases such as fire impossible to avoid and explosions before approach. Reality imposed itself. But it was too late to reverse what had already been lost months earlier, when they chose not to believe what they saw. In the next chapter, the war approaches the ground, because after dominating the sky, proximity fuses would be used where no one expected it. In infantry battles, and what was created to shoot down planes, it would begin to decimate soldiers hiding in forests, even in the most feared of them, the Ardennes. James Van Allen was 28 years old when he was called for a project that at first glance seemed impossible. The task was clear: to create a vacuum tube so small and tough that it could survive the firing of a 5-inch cannon, withstanding a force of more than 20,000 times gravity. In 1942, this was equivalent to asking electronics to perform acrobatics inside a bullet. Van Allen, a newly graduated physicist with a specialization in electronics, was not a household name. There were no medals on his chest, no patents filed in your name, but he accepted the mission, and within a few months he delivered to the T-section something that most scientists thought unfeasible: a functional, miniaturized electronic tube shielded with special glass and capable of operating for fractions of a second, long enough to perceive the approach of an enemy plane and command an explosion. From this tube was born the heart of the proximity fuse, a radar inside a grenade, an electronic eye with time to think. Van Allen did not receive headlines nor tributes, but his tube became standard. More than 80 million were manufactured by the end of the war, and without it, the projectile would remain blind. What Van Allen created wasn't just a technical piece, it was the foundation of a paradigm shift. For the first time, an electronic circuit was placed inside a disposable ammunition. This required not only miniaturization, but also absolute reliability. The tube needed to work even with extreme temperature variations, violent impacts, and electromagnetic interference. To do this, Van Allen developed new sealing methods, reformulated materials, and created an internal self-compensation system, all without computers, just calculations, oscilloscopes, and physical intuition. When the piece was subjected to the field firing test, it not only resisted, it worked perfectly. It exploded at a calibrated distance from the target, at the right time, at the right angle. The laboratory applauded, but the world never knew. The historical irony is that the same Van Allen, 2 decades later, would become a world-renowned name as he led the scientific mission that would discover the radiation belts that surround the Earth. But in 1943, he was just a young engineer working quietly, creating what most physicists still considered fiction. His name was not mentioned in the military reports, not even in the victory speeches, but every plane shot down by a proximity fuse, every V-1 bomb destroyed in the sky over London, every soldier saved on dry land, it all started inside that small glass tube. It is important to remember that without this piece, the whole concept of radar embedded in ammunition would be just theory. It was the physical limit of the time. The radar already existed, but it was the size of a room. The challenge was to miniaturize it, to fit into something smaller than a thermos. American industry has invested heavily in this transformation. New materials, new manufacturing processes, new design doctrine. And it was in this environment that Van Allen flourished. His mind combined precise mathematics with applied creativity. He understood that war did not give time for perfection. It was necessary to create something that worked well enough, fast enough, and that could be produced by the millions. And that's what happened. Van Allen tubes became the internal standard for all proximity fuses manufactured until the end of the war. The factories operated 24 hours a day. Every minute, dozens of circuits with his invisible signature were inserted into warheads that would cross the world to defend ships, cities, and forests. It was the victory of applied science, and also the symbol of a new form of heroism. No longer that of the soldier with a rifle, but that of the anonymous engineer with pencil, ruler, and welder in hand. On the other side of the Atlantic, Germany was still insisting on the search for miraculous weapons, super-heavy tanks, ballistic missiles, jet planes, but none of these projects were functional on a large scale. What the Americans did was different. They did not look for the perfect weapon, but the weapon that worked on all fronts. And above all, that it could be reproduced without depending on genius. Because Van Allen was, yes, a genius, but his greatest virtue was to create something that others could replicate. He did not want to be irreplaceable. He wanted to be useful. The impact of this was not only military. At the end of the war, the technology developed for fuses would be adapted for a new generation of electronic devices. Circuit miniaturization, industrial assembly standards, and even endurance testing would become the basis for future space missions, modern computing, and digital navigation systems. And it all starts here, in a glass tube fired from a cannon. In the Section T files, there is a note signed by a technical officer. Without the Van Allen tubes, this project would not have left the paper. Curiously, Van Allen himself, years later, will report in interviews that he considered this phase of his career just a necessary service. And maybe it was, but it was also decisive. In the next chapter, we'll look at where these pipes found their most devastating use, not in the skies, but among the frozen trees of the Ardennes. Because there, in December 1944, the German infantry discovered that the American artillery had learned to think, and that hell could come from above, even when the enemy was not seen. At the beginning of the war, Japanese naval doctrine was based on one clear advantage: its pilots. Veterans of the war in China, trained in real combat, experienced in offensive maneuvers, tactically superior. Japan did not have industrial superiority, nor logistical dominance. But in the air, his squadrons operated with lethal precision. American ships knew what it meant to face a coordinated attack by dive bombers and fast fighters. It was a doomsday of destruction, unless a full squadron of escorts and fighters was on high alert. The rule was clear: no ship survives in isolation, until that rule began to crumble. In 1944, the USS Columbia was sailing south of Leyte when it was surprised by a multiple air attack. The anti-aircraft batteries fired as usual. But there was a detail. The guns were loaded with the new projectiles with proximity fuses. The result was immediate. 6 planes shot down in less than 3 minutes. No impact on the hull, no request for reinforcement. For the first time, a light cruiser had single-handedly repulsed a full-blown air attack. No air cover, no losses. Without hesitation. The change wasn't just tactical, it was philosophical. Until then, anti-aircraft artillery operated on the basis of saturation, firing as much as possible at the highest possible density and hoping that some projectile crossed the path of the target. It was a war of probability. With proximity fuses, this has changed. Now each shot had a rudimentary brain, a decision, a criterion. The gunners ceased to be just metal operators and became administrators of embedded intelligence. The slaughter rate has increased. Ammunition consumption has fallen. Logistical efficiency has skyrocketed. The doctrine has changed. The Japanese took notice. As the months passed, his squadrons came back increasingly empty. The veterans, irreplaceable men, were being slaughtered by a defense that did not make mistakes. The Imperial Air Force began to review its reports. The standards didn't match. The evasive maneuvers, once effective, now seemed useless. An experienced pilot, upon returning from a mission, wrote, "They know where we are going to be before we arrive." But it was not a premonition. It was science. The fuse measured the speed, interpreted the return of the radar signal, and detonated as close as possible to the target. He didn't need to get it right, I just needed to get close. The consequence was dramatic. In 1943, the average number of Japanese planes lost per mission was 11%. In 1944, it jumped to 47%. In some attacks, such as the Battle of Leyte Gulf, it exceeded 70%. Japanese aviation quietly collapsed, not for lack of courage, but for lack of a future. Each veteran pilot shot down was a decade of training lost, and no simulator replaced the real experience. Japan has begun to accelerate emergency training programs. Recruits with only 30 hours of flight time were sent to the front. Many did not even know how to return to the aircraft carrier. The war, once won by wings, was now won by sensors. The Americans understood what they had in hand. Naval defense doctrines were reformulated. The fleet began to operate in more dispersed formations, less interdependence, more autonomy, each ship with its own defense bubble. It was the beginning of embedded electronic warfare. Instead of escorts, they used algorithms. Instead of external radars, they used internal eyes. And Van Allen's logic imposed itself. It was not necessary to think fast. It was enough to program beforehand. Meanwhile, the Japanese command debated alternatives. Technical reports pointed out that the American defense was evolving at an unmatched pace. Attempts were made to change the routes, flying at irregular altitudes, attack at unexpected times. Nothing worked. The shots came, and they hit. The morale of the pilots plummeted. Some refused to take off. Others flew in absolute silence, with no hope of return. Japan had not yet officially started using kamikazes, but the reality imposed by the proximity fuse made air death almost inevitable. It was just a matter of accepting fate. The Pacific Theater, hitherto dominated by surprise attacks, was now controlled by a silent defense. War ceased to be a matter of maneuver and became an equation. The enemy who believed most in the force of will faced, without understanding, the force of mathematics. Guided warfare had arrived, and it didn't need to be seen to be felt. At the heart of this new paradigm was American industrial capacity, because it would be of no use to invent Van Allen, to have the courage of Churchill or the calculations of Section T if the United States could not sustain this weapon in the field. But they could, and they did. By 1944, the US was producing 2,500 fuses per hour. Every hour, more than 1,000 electronic eyes rolled off the assembly lines, ready to embark for the Pacific. It was a production line of lethal predictability, a statistic with gunpowder. In Japan, senior officers began to suggest that the problem was spiritual, that the Americans had dominated the war because they had abandoned doubt. But it was not faith, it was physical. And in the face of this, not even fanaticism could resist. The doctrine of mass attacks has lost its raison d'être. Each squadron sent was a death sentence, and the Empire knew, in the next chapter, precision would come out of the sea and take to the skies even more lethally, because the next step in the evolution of fuses would be their full integration with strategic bombing, and the city that would be chosen as an example would not survive. October 1944. The Battle of Leyte Gulf marked not just a military turning point in the Pacific, but a psychological breakdown. For the first time, the Japanese High Command was forced to admit in unofficial terms that the Empire's air doctrine was bankrupt. The reports were clear. Entire bomber formations were being destroyed before reaching the target. In many cases, before even seeing the enemy. It was a new kind of defeat, silent, invisible. The pilots fell without knowing where the shots were coming from, and even when a plane managed to break through the defensive blockade, the damage was minimal. The human cost was absolute. Tactical effectiveness was nil. It was then that a new proposal emerged, not from engineers or strategists, but from officers desperate for immediate results. To turn the aircraft itself into a weapon, not with bombs, but with the pilot. Under the weight of collapse, kamikaze logic was born, not as an honor, but as the only remaining resource. The decision did not come from above. It was brewing in the middle levels of command, where the pressure was greater and the expectation of victory had disappeared. The data no longer lied. The slaughter rate was 54% per mission. With the new American defense model based on proximity fuses and interconnected radar, even suicide maneuvers had become predictable. American fighters intercepted squadrons before the line of attack, and when one or two planes managed to escape, they were greeted by a cloud of artillery that thought. An invisible curtain that required no contact, only approach. The psychological impact of this was devastating. Japanese pilots trained for precision missions were being reduced to statistics. They were destroyed before making any difference. Suicide, then, appeared not as an ideology, but as the only chance to cause harm. The first official kamikaze mission was launched on October 25, 1944, against the USS St. Lo. The impact was direct. The ship sank. There was celebration in Tokyo. But in the U.S. Department of Defense, the event was not interpreted as a sign of strength, but as proof that the enemy had abandoned logic. The technical analysis carried out by the Pacific Command pointed out that the attack was only successful due to failures in early detection and momentary absence of anti-aircraft cover. In other words, it was an accident. The following missions proved this. With each new suicide attack, American defenses adapted. Proximity fuses became even more accurate. The batteries received updates, the doctrine adjusted, and the impacts decreased. In just 2 months, the success rate of kamikazes dropped to 15%. For every ship hit, 10 planes smashed into the sea without ever getting close. Most exploded in mid-air, detonated by sensors that detected their approach from hundreds of meters. Sacrifice became ineffective. Technology overcame even despair. And the most ironic thing is that while Japan sacrificed its children in an attempt to pierce an invisible shield, the US continued to manufacture 70,000 fuses a day, with quality control, logistical distribution, and constant technical updates. It was the defeat of faith by statistics. The Japanese doctrinal collapse was not immediate. It was gradual, like a boat being engulfed by currents it does not see. As the results of the kamikazes became less relevant, the leaders tried to justify their continuity on moral, patriotic, or spiritual grounds. But behind the scenes, the truth was clear. They had no other choice. The industry was in ruins. The veteran pilots had been decimated, the airfields were under constant attack, and new generation fighters, such as the Kai-84 and Shiden-Kai, could barely take off due to lack of fuel or parts. Only the fanatical youth remained, and the promise of posthumous glory. Meanwhile, on the American aircraft carriers, defense doctrine became increasingly refined. Proximity fuses were integrated not only into primary batteries, but also into automated defense systems. The time between detection and firing was seconds. And with each thwarted attack, new data fed into the continuous improvement systems. The war had become a laboratory in real time, and the Japanese, without realizing it, were the unwitting guinea pigs. A secret Japanese document from February 1945 records the following phrase, attributed to a frustrated officer after yet another failed mission. "We are throwing pearls against a wall of steam." The metaphor was accurate. American technology was invisible, impersonal, and absolutely impenetrable. It didn't matter how much the pilot believed in his mission. The wall saw no honor. He saw only proximity, and it exploded. The result of this equation was devastating. More than 3,000 kamikazes were launched between October 1944 and August 1945. Of those, less than 20% managed to cause any significant damage. The human cost was irreparable, and the strategic impact? Almost nil. The American fleet continued to advance, island by island, with calculated losses replaced in days, supported by an industry that did not stop. And all of this was supported by weapons that didn't need to hit. Just think before they exploded. In the next chapter, we'll look at the apex of this logic, when the proximity fuse becomes the protagonist of a brutal ground campaign. In the forests of the Ardennes, American technology descends from the sky and turns artillery into an eye of God. A weapon that not only saw but chose where to kill, and that, in 3 minutes, would forever change the tactics of war on European soil. Antwerp, late 1944. The largest Allied port in Northern Europe had become a priority target of German retaliation. It was not a symbolic city, but a critical logistical artery. If Antwerp fell, the Allied advance would freeze. And Hitler knew it. Therefore, he personally authorized the largest V-1 missile campaign ever recorded. There were more than 4,900 launches in just 3 months, all directed to an area of less than 60 square kilometers. It was a mathematical bombardment. The German doctrine bet on volume, repetition, and wear, but there was one factor they didn't foresee. The skies over Antwerp were armed with science. The operation to defend the city became a milestone in the history of modern warfare. For the first time, tracking radars, anti-aircraft batteries equipped with proximity fuses, electromechanical firing directors, and real-time logistics operated as one organism. The city was surrounded by an invisible shield that learned with each impact. What once required dozens of shots was now resolved in 2 or 3. Within weeks, the interception rate jumped from 40%, already considered impressive, to more than 91%. A statistic that the German commanders themselves refused to believe when they received the first reports. Some classified the data as psychologically manipulated. But it was not manipulation. It was radar. It was physical. It was American mathematics in its raw state. To get an idea of the contrast, Germany's total production of V-1 missiles was about 30,000 units. The United States, in just 2 years, produced more than 22 million proximity fuses. That's right, 22 million, with the capacity for immediate delivery in multiple theaters of war simultaneously. And all this with electronic quality control, field tests, and real-time embedded distribution systems. The Germans launched rockets that they could not guide. The Americans responded with ballistics that he thought. If you were impressed by this number, comment below, "Shocking data." Because the war was won even before the missiles took off. What Antwerp revealed to the world was not only the power to shoot down targets, it was the power to control the environment. Air defense has become a symphony of precision. Radars tracked the V-1 more than 80 kilometers. Analog computers calculated the exact point of interception. The batteries fired with millimeter synchronization, and at the right moment, the projectile exploded not at the touch, but at the approach. The missile disappeared before crossing the line of impact. Often, citizens did not even hear the noise. They saw only the flash in the sky and the absence of destruction on the ground. This operation was only possible because the United States had merged science, industry, and doctrine into a single operational structure. The firing directors used in Antwerp, such as the M9, were coupled to SCR-584 radars and integrated directly into the Bofors guns and the 90mm howitzers. Each element of the chain talked to the other, a closed system of automated precision. The human operators only had to follow the protocols. The rest was done by the machine. It was the embryo of modern electronic warfare. An unthinkable concept for the Third Reich, whose industrial structure still depended on decentralization, local decisions, the figure of the isolated genius technician. While the Germans trusted the lab engineer, the Americans trusted the factory engineer. And the results were not limited to interception. With the city secure, Allied convoys were able to unload tons of supplies, weapons, ammunition, and fuel on a daily basis. Antwerp has become the largest logistics base on the continent. A post-war study demonstrated that without the defense of Antwerp, the advance toward Germany would have been delayed by at least 6 months. And that window could have been enough for the Reich to complete the development of experimental nuclear weapons. What was at stake was not just a city, it was the very timing of victory. The Germans, powerless in the face of this invisible wall, tried to adjust their tactics. They varied launch times, altered trajectories, created missiles with irregular timing. Nothing worked. American logic was adaptive. With each new trick, the systems learned. Each week, the efficiency rate increased. It was an asymmetrical war in its purest sense. On one side, a collapsing empire betting its last chips on unleashed bombs. On the other, a nation that not only produced but understood. Not only did he shoot, but he anticipated. Not only defended, but processed. Antwerp, in the end, survived. The port continued to operate, the troops advanced, and the V1s that crossed the English Channel became vestiges of a failed strategy. Germany, which had bet on technology as a differentiator, was defeated by a technology that refused to appear in the headlines. No one saw the proximity fuse, but he was everywhere. In each explosion ahead of time, in every missile shot down in the sky, in each train that did not stop advancing. In the next chapter we cross the Rhine, because now the war is moving to German soil, and there the same sensors that shot down planes and deflected bombs begin to transform ground-based artillery. The German soldiers will see the impossible, death from above, without warning, without contact, without error, an artillery that read the field, and it exploded before it touched the ground. Germany's scientific collapse was one of the most bitter ironies of World War II. The country that had produced giants like Albert Einstein, Werner Heisenberg, and Max Planck, names synonymous with innovation and scientific excellence, was unable to create something simple and crucial, a functional proximity fuse. How was this possible? The answer lies not in the lack of brilliant minds, but in the dysfunctionality of a system plastered by internal rivalries, ideological control, and an institutional fragmentation that opposed collaboration. The scientific structure of the Reich was, in essence, a network of watertight compartments. The Luftwaffe, the Kriegsmarine, the Heer, and the SS developed their own independent projects, with limited resources and without any centralized coordination. Not only did this dilute efforts, but it also resulted in duplication of work, failures to share findings, and the loss of valuable time on ineffective experiments. Each armed force worked with its own agenda, and often in total disregard for what the others were doing. Even within a single institution, there was a constant struggle for funding and prestige, an environment where self-centeredness and destructive competition were more common than the spirit of collaboration. Meanwhile, in the United States, the situation was radically different. The country, driven by a massive war effort, brought together the largest universities, government agencies, and industries under a single coordinated command. The Manhattan Project, which would create the first atomic bomb, is the most notorious example of this collaboration. But the same spirit of integration was applied on other fronts, including the development of proximity fuses. Universities, such as Johns Hopkins University and the Carnegie Institution, have worked directly with the defense industry to turn academic ideas into practical technologies. The government centralized research and development, creating an interconnected innovation network fueled by immense industrial power. And here's the irony. While Germany, with its vision of efficiency, allowed fragmentation and ideological control to take over scientific research, the United States, in a seemingly more flexible and democratic system, managed to unite science and industry in an extraordinary way. Ideological control that limited scientific freedom in Germany was one of the greatest failures of the Nazi regime. The military leaders' distrust of civilian scientists, coupled with the party's tight control over academic thinking, created an environment where innovative ideas were stifled, while research projects were often aborted for political reasons. The lack of a unified strategy meant that even the most promising ideas were overshadowed by internal disputes. In the United States, the environment was radically different. Collaboration between scientists, engineers, and industrial manufacturers has enabled the creation of proximity fuses that in a matter of months have gone from paper concepts to mass production. And this effort was decisive. The mass production capacity of the United States outpaced any German attempt to replicate such a scale, despite attempts at parallel research in the Axis powers. Although German scientists made initial attempts to develop proximity fuses, a lack of inter-institutional coordination and adequate resources prevented them from achieving any real breakthrough. The fragmentation of German science has had a devastating impact on its ability to innovate. Scientists were at best working in isolation and at worst battling each other for resources and recognition. This prevented any significant progress. Meanwhile, the United States had a research infrastructure that not only supported scientists, but also provided the industrial capacity needed to turn these innovations into real weapons. This structure allowed the US to respond quickly to war needs, while the Germans were struggling to coordinate efforts that never materialized effectively. While German scientists, such as the famous physicist Werner Heisenberg, were steeped in ideological and scientific dilemmas, the United States was busy developing a smart weapon, a projectile that thought on its own. What the Germans failed to realize was that the real power lay in uniting scientific thinking with industrial production capacity. Not only did this make the US faster and more effective, but it also gave them an undeniable strategic advantage. Here is the shocking fact that the Germans ignored. American production of proximity fuses was 10 times greater than the capacity for development and production of any comparable technology in Germany. With more than 70,000 fuses produced per day until 1944, the United States had a capacity that the Reich never reached. This capability not only outperformed German designs, but also revealed the structural flaw that led to a vicious cycle of inefficiency and underestimation. The US, logistical, industrial, and scientific superiority was not just a matter of volume. It was the ability to turn innovation into action on a scale never seen before. If you were surprised by this number, comment below. Logistics wins, because in the end, it was this massive force that turned the tide, and from that moment on, air war and ground war would no longer be fought in the same way. Germany, still with its antiquated vision of efficiency in a fragmented system, was about to face the last card of the Allies, the fusion of scientific thought with mass production. In the next chapter, we'll explore how proximity fuses have changed artillery on the ground battlefield. If planes were already being shot down in a clever way, now soldiers on the ground would experience the accuracy of these thinking munitions. The future of the war was taking shape, and Germany was already without answers. As the great American industrial machine gained momentum, a quiet and often forgotten history unfolded in the factories. Those who saw proximity fuses as symbols of precision and scientific innovation may not have known that behind this technology were the anonymous hands of thousands of workers, many of them women, who, with extreme dedication, welded each tiny piece of the components without knowing the magnitude of their work. They were responsible for transforming the ideas of scientists and engineers into real and practical weapons, capable of changing the course of war. These women, many of whom were newcomers to the workforce due to the need for a workforce during the war, were a silent force in a war effort that involved all layers of American society. In converted factories, such as the Sylvania and Crossley Corporation facilities, they worked long hours in extremely difficult conditions, assembling proximity fuses that were mostly small enough to fit in the palm of a hand. With precision tools, they soldering tiny circuits and connectors, immersed in a production that, for them, was only one part of the war effort. Unknowingly, these workers were playing an essential role in the Allied victory. Each proximity fuse they mounted was not just a technological object. It was a key to shooting down enemy planes to ensure the survival of the Allied forces in combat. They were directly linked to a grandiose feat, but unlike the scientists and engineers whose names would be remembered, they would be almost invisible in history. His contribution was not celebrated with medals or public recognition, but without them, American victory would have been much more difficult to achieve. The technology these women helped create was not just a scientific marvel, but an industrial achievement that depended on a massive effort of scale. The massive production of proximity fuses was, in fact, a reflection of American wartime industrial capability. While German factories struggled with material shortages and a lack of coordination, the United States was able to quickly reconfigure its economy to produce not only in large quantities, but with unbeatable accuracy. Thousands of female workers, who had initially been excluded from certain industrial sectors, were now playing a crucial role in modern warfare. Not only did it save lives, but it forever changed the nature of industrial warfare. However, there was a human cost. Constant exposure to beryllium, a metal used to manufacture certain components of fuses, resulted in a hidden tragedy. Many of the workers who handled beryllium without proper protection suffered from severe respiratory diseases years later, a devastating consequence of working in poor conditions. Beryllium disease, an incurable lung disease, has affected hundreds, perhaps thousands of workers. They were paying an invisible price, their health sacrificed by the war effort. The women who spent hours welding tiny pieces of beryllium were contributing to the victory, but many of them would pay with their lives for decades to come. This tragedy is often overlooked in traditional narratives about World War II, which tend to focus on military victories and technological innovations, leaving aside the human sacrifice that made those victories possible. The true cost of the war was not only the death toll on the battlefields, but also the invisible suffering of the women and men who helped create the weapons that would defeat the Axis. Each proximity fuse, with its deadly precision, was the product of a collective effort that involved both the brains of the scientists and the hands of the workers. They were the true unsung heroines of this story, unaware that they were participating in one of the greatest industrial feats in modern history. Still, the memory of these women was largely erased until years later, when beryllium disease began to affect a growing number of former defense industry workers. Only then, after decades of suffering and with a lost generation, did the recognition come. Although it was not possible to completely repair the damage done to those lives, the efforts of the workers had a lasting impact. Their legacy is in many ways tied to America's ability to turn its industrial efforts into concrete battlefield victories. But it also reminds us that behind technology and great achievements, there is always the human price. This chapter of history is a reminder that war, while widely known for military confrontations, is also a war fought behind the scenes of industry and production. The real strength of the United States, which allowed the creation of a mass proximity fuse, was the ability to mobilize the whole of society, from the most brilliant scientists to the anonymous working hands. This joint effort, which involved not only the men on the front lines, but also those in factories and laboratories, was what secured the Allied victory. But, like every story of triumph, this one also has its dark side. Now, with the war nearing its peak, let's see how this industrial effort translated into real changes on the battlefield, and how the Axis forces began to realize too late that the American advantage lay in a new logic of warfare, where precision and scale were the new weapons. In the next chapter, we'll explore how proximity fuses transformed ground artillery, creating a new era of intelligent combat that Axis enemies weren't ready to tackle. The United States, with its unmatched industrial prowess, was not just at war on the battlefield. They also waged a silent battle in the field of counterintelligence, using a network of deceptions and strategic protections to ensure that their most valuable secrets remained out of the enemy's reach. In the case of the proximity fuse, security was not just a matter of keeping the prototypes out of the hands of the Germans, but of involving the entire nation in an effort of absolute secrecy. The American government created a complex system of dissimulation and protection, with protocols so strict that they bordered on the paranoid. Most of this security system was geared towards ensuring that the proximity fuse design remained secret, without enemies knowing what it was about. Every part of the device, from the tiny antenna to the vacuum tube that allowed it to detect the target, was under constant surveillance. And in an effort to confuse any attempt at espionage, the United States was not content to just isolate the project. It surrounded it with a web of deception, creating false code, misinformation, and camouflage names for the prototypes. The paranoia surrounding secrecy ran so deep that inside the labs, scientists were constantly subjected to rigorous inspections. The FBI was called in to conduct thorough checks on researchers and facilities, with ruthless security checks to ensure that no information leaked. It was such a closed operation that scientists often did not know the full extent of the technology. They were simply in charge of one part of the process, without ever seeing the full picture. The transport of the fuses was also handled with extreme care. Each unit was escorted by armed security teams, with protocols that looked like something out of a spy novel. Proximity fuses were transported in closed trucks, and even the routes were kept secret, with frequent changes to avoid any possibility of interception. In addition, the factories involved in the production of the fuses were guarded with constant surveillance. An oversight could even result in a strategic disaster. If someone was caught with a proximity fuse, the protocol was clear: self-destruct. Each fuse unit had a built-in self-destruct mechanism, which completely destroyed the device and its information as soon as the capture attempt was detected. This ensured that no parts fell into the wrong hands, and that even if something was intercepted, the enemy would never have access to the technology inside. In 1944, however, the war reached a critical point. During the Battle of the Bulge, the Germans managed to capture a large stockpile of proximity fuses that belonged to an American ammunition depot. There were about 20,000 units, an impressive number, and yet what could have been a strategic turn for the Third Reich turned out to be a monumental mistake. Despite having in their hands the most valuable secret of modern warfare, the Germans simply did not understand what they were seeing. The scientists and engineers of the Reich, who had developed some of the most advanced technologies of the time, looked at the captured fuses with skepticism. They simply did not believe that the United States could have developed something so sophisticated, so innovative. The idea that an industrial democracy could create such a precise and complex weapon seemed unimaginable to them. German arrogance, which believed in an ideological and technological superiority, blinded them to the truth that was before their eyes. German scientists analyzed the fuses and dismissed them as a hoax, an American propaganda, something that could not work, without realizing that they were, in fact, facing the first real, smart weapon in history. The refusal to accept the possibility of such a great technological advance on the part of the Americans was a fatal mistake. The Germans were so immersed in their own doctrines of war, so confident in their technical and philosophical approach, that they could not adapt to the speed and innovation of the adversary. Meanwhile, the United States continued to mass-produce the technology that was changing the war. The flexible mindset, the ability to unite science, industry, and defense allowed the Americans an advantage that the Germans, trapped in the fragmentation and rigidity of their system, could never achieve. The irony of this story is that although the Germans had captured the proximity fuses and were theoretically in possession of the greatest technological advantage, their inability to understand what they had in their hands prevented them from reacting effectively. The solution was before them, but ideological bias and a lack of strategic vision prevented them from seeing reality. And so, the weapon that could have turned the tide of the war against the Allies was forgotten, misinterpreted, and ultimately unused. Now, as the United States continued to turn the theory into a devastating reality, the Allies were about to see the real impact of this innovation on the battlefield. In the next chapters, we will witness how the superiority of proximity fuses would drastically change the rules of war. From the defense of London to the crucial clashes in the Pacific, the technology that the Germans underestimated would begin to prove unsurpassed. In December 1944, the Ardennes became a testing ground for the most innovative application of modern artillery. The end of the trenches, a military doctrine that had endured for centuries, was about to happen. For the first time in the history of ground warfare, precision aerial artillery would become the decisive game-changer. The Battle of the Bulge, the last major German offensive on the Western Front, was about to be marked by the debut of proximity fuses in ground combat, a choice that would be both tactical and morally risky for Americans. Up to that point, ground warfare still relied heavily on traditional artillery tactics, large barrages of fire, with the shells hitting targets by direct impact, with low accuracy but great range. The trenches and protective shelters had been the defensive pillars of the war, but nothing could prepare the German soldiers for what was about to happen. In an act of sheer necessity, American artillery was equipped with proximity fuses, tiny radar devices capable of detecting distance to a target and firing at the optimal moment, regardless of where the projectile landed. This technological innovation changed the rules of war. When the first firing was carried out with the proximity fuse, the airburst not only caused destruction, but also rendered all known defensive strategies obsolete. The above-ground detonation, instead of directly hitting the target, spread lethal fragments into a death cone, capable of hitting any soldier, regardless of their position. Trenches, bunkers, and even armor, which had previously protected the troops, proved powerless against a new era of clever artillery. The impact was immediate and devastating. The decision to release the technology for ground combat was fraught with risk. The capture of a single proximity fuse shell in the hands of the enemies would have compromised the strategic advantage of the Allies. But the urgency of the situation made the American High Command choose to use the weapon. The fear of losing the technological edge was overcome by the urgent need to repel the German attack, and the results proved that the choice was right. In the space of a few hours, hundreds of German soldiers were killed, not by shells that directly hit their positions, but by a shower of fragments falling from the sky. The resistance was annihilated not by direct physical impact, but by the brutal accuracy of a weapon that thought before it exploded. The psychological impact on German troops was equally profound. The units advancing in the Ardennes, confident that their old tactics would suffice, began to wonder how they could fight off a technology that seemed to come from the future. Captured soldiers would later describe the feeling of being in an unequal fight against an enemy that had already pushed the boundaries of known technology. "We are fighting against the future," some said, acknowledging that they were facing a military innovation that made their most grounded doctrines obsolete. And that was just the beginning. As the fighting intensified, the Germans began to realize that their resistance could no longer be sustained against a force that used technology so accurately and deadly. American artillery units, previously limited to bombarding areas and waiting for hits, now attacked with surgical precision, maximizing the effect of each shot. Every shell fired with a proximity fuse was a death sentence that never failed. By comparison, German shells that still relied on conventional fuses were ineffective, unable to penetrate American defense lines that now operated in a more coordinated and efficient manner. The land war, which until that moment had been marked by brutal and bloody battles on the ground, experienced a historic turning point in that icy December. Proximity fuses didn't just change the battlefield. They redefined modern warfare. Military doctrines that had been refined over centuries were overturned in a matter of hours, replaced by a logic of precision and speed that the Germans could not comprehend, let alone replicate. Trenches, fire saturation tactics, and armored shelters became useless in the face of technology that in itself made war faster and more lethal. What happened next was not just the defeat of an army, but the collapse of a way of thinking about war. The psychology of the German troops was profoundly shaken. They were being decimated not by superior numbers or conventional firepower, but by technology that seemed to have been designed to cause them maximum pain and confusion. The concept of battle, as the Germans knew it, was disappearing before their eyes. The new reality was relentless. Winning no longer meant having more soldiers or more weapons. It meant having more intelligence and more production capacity to make these innovations a reality. This historical moment in which land warfare was transformed by a simple decision to use technology not only defined the fate of the Battle of the Bulge, but also illuminated the way for the future of warfare. Combat tactics evolved, and clever artillery would become an essential pillar in modern warfare. The future had arrived, and armies that lacked the ability to innovate quickly were doomed to defeat. The Germans, until the last moment, maintained their beliefs that the war could be won by strategies that had worked in the past. However, the close-fused combat system proved to be such a significant game-changer that the German response to it would come in one last, desperate act of sacrifice, the kamikaze. But the true story of the proximity fuse was yet to be revealed. She was about to change the course of the conflict even more. And as German troops found themselves outclassed by American technology, the world was beginning to understand that great victories would no longer be just a product of bravery on the battlefield. They would be a reflection of how a nation could mobilize its industrial and scientific capabilities to prepare for the wars of the future. In the next chapter, we will see how this innovation would manifest itself in the naval battles of the Pacific, where the logic of proximity artillery would become the most decisive secret weapon of warfare. The year was 1943, and the world was immersed in World War II. Amid the ferocity of the fighting, a quiet technological development was poised to redefine the future not just of wars, but of industry and science on a global scale. The proximity fuse, a seemingly simple but impact-revolutionary device, was the precursor to modern smart weapons, a milestone that would span decades of military and civilian innovations. Until then, Artillery relied on calculations and manual actions. A traditional projectile required the analysis of the target and a series of corrections based on the estimation of the impact. But with the invention of the proximity fuse, the rules changed completely. For the first time, a device was designed to think, to make decisions based on a radar programming that allowed the projectile, as it approached a target, to detonate automatically. This small advance on the battlefields not only altered the dynamics of warfare, but also opened a new chapter for electronic engineering, microelectronics, and ultimately what we now know as smart weapons. The truth is that the fusion of science, technology, and industry had implications beyond the borders of war. What many saw as a simple instrument of destruction would become one of the greatest technological legacies of the 20th century. The miniaturization of circuits, the development of proximity sensors, and the ability to create autonomous systems that could operate without direct human intervention were the seeds planted during those critical years. The proximity fuse was not just a weapon, but the point of origin of a line of innovations that would make its way into our everyday lives. American scientists and engineers, by bringing this technology to life, laid the foundation for what would become, in the following decades, the revolution of detonation systems, guided missiles, and even the smart bombs used in contemporary conflicts. It was a technology that no longer depended on mere brute force, but on precision and the intelligent choice of the moment of intervention. This principle, developed in secret during the war, would expand to other fields, such as aviation, missile defense systems, and even space programs. The radar that initially helped locate enemies was now integrated into devices capable of guiding not only ammunition, but also interplanetary missions. With the end of World War II, innovations developed for military purposes would quickly become civilian applications. The same process of miniaturization and precision that made weapons more effective was also applied to the electronics industry. The same technology that helped create more sophisticated defense systems drove the emergence of integrated circuits and microprocessors, which in the 1950s would begin to be used in commercial computers. The communication and computing industries have taken a leap forward due to the legacy left by the manufacture of proximity fuses. What was once a military invention would become the backbone of the digital revolution that would follow, enabling everything from modern computing to the creation of consumer electronic devices that became ubiquitous. In fact, the production of proximity fuses was a clear example of how industrial-scale efficiency and technological innovation can intertwine. In the early days, American factories were producing thousands of units a day, a pace that not only met military demand, but also set a standard for excellence and speed in mass production. This large-scale production process would become the basis for post-war industrial systems, influencing both the military and civilian sectors. The ability to manufacture technological products accurately and quickly became a hallmark of the United States, and it was in large part what helped cement its position as an industrial leader in the 20th century. Military innovation was not limited to war. With the growth of the defense industry in the United States, knowledge transfer and advances in the design of complex systems have allowed for the development of new technologies for peaceful purposes. The proximity fuse paved the way for the creation of satellites, rockets, and even GPS navigation systems, which use similar principles to guide and achieve objectives accurately. The legacy of the fuse is present in virtually all of today's cutting-edge technologies. In addition, we cannot forget the transformation of the concept of intelligence into weapons. The proximity fuse was undoubtedly one of the first manifestations of what we now know as smart weapons. The development of autonomous weapons, guided by radar systems and sensors, began a trajectory that would evolve into missiles and drones. These, in turn, would influence modern warfare by making battles faster and more impactful, while reducing risk to combatants. The impact of this small but mighty device reverberated on several other fronts. The future of precision weapons, with programmed and intelligent detonation systems, was mapped out on the US production lines during World War II. But this future was not limited to the military field. The technology that the US developed, driven by the necessity of war, spread to the space sector and the electronics industry. The emergence of miniaturized circuits, based on the fundamental principles of the proximity fuse, has opened the door to the creation of more compact, efficient, and intelligent devices, which would be indispensable in everything from national defense systems to our everyday lives, through smartphones, computers, and even self-driving cars. This advance in the field of precision and technological miniaturization not only altered the way wars would be fought, but also forged the foundation of a world in which the line between military use and civilian innovations would become increasingly blurred. The legacy of the proximity fuse, therefore, cannot be underestimated. It was the starting point for the technological revolution that extends to the present day, shaping, among other things, the weapons we see in modern conflicts, but also the smart devices we use on a daily basis. As we look to the future, the question remains, what will come next? What will be the next technological frontier that, like the proximity fuse, will change the world in ways we can't yet imagine? The next step in the history of smart weapons and precision technology is already underway, and as in 1943, the line between the battlefield and everyday life continues to be blurred. The proximity fuse, the weapon that changed the course of the war, was not just a technical breakthrough, but a reflection of a system that valued freedom, collaboration, and innovation. Its creation and success cannot be explained solely by scientific brilliance, but by the environment in which it flourished, a democratic environment that encouraged the exchange of ideas, cooperation between distinct sectors of society, and, crucially, the appreciation of collective intelligence. When we look at the impact of the proximity fuse, we see much more than a military invention. We see the expression of a culture that allowed for freedom of thought, open science, and effective coordination, a system where creative minds could work without the shackles of a totalitarian regime. While the United States was investing in its industrial, scientific, and logistical capacity to mass produce, and efficiently, Germany was stuck with an ideology that limited and fragmented its ability to innovate. The Nazi regime not only pursued political and cultural freedom, but also stifled creative potential within its own industry and science. Institutional fragmentation, ideological control, and internal competition between military and scientific forces prevented Germany from developing something that the United States, working collaboratively, achieved in a relatively short time. The proximity fuse, as simple as it may seem, represented the contrast between two forms of social organization. In the United States, scientists, engineers, military and industrialists came together to solve a common problem, while in Germany, fragmentation and authoritarianism destroyed any possibility of genuine cooperation. This contrast is not only technical, but deeply philosophical. The democratic model of the United States, with its universities, factories, and government agencies working in tandem, produced not only a fuse, but the mindset and methods that would lead to the creation of modern technologies. Each stage of the weapon's development was linked to a process of freedom, freedom to research, freedom to experiment, and freedom to fail, something that the Nazi regime, with its obsession with control, could never offer. Freedom of thought, without the limitations imposed by ideological censorship, was what made it possible to create something so sophisticated, an innovation that the Germans, even when they had it in their hands, could not understand or replicate. This contrast between democratic creation and totalitarian destruction is what makes the story of the proximity fuse not only a technological lesson, but also a lesson in values. The war was won not only by the technical superiority of American weapons, but by the culture that created them. The proximity fuse was, in essence, a symbol of the strength of democracies. It arose from a system that, unlike totalitarianism, encouraged creativity, collaboration, and adaptation. The ability of the United States to mobilize its scientific and industrial resources to solve problems in an agile and coordinated manner was one of the keys to success in the war. The Germans, with all their ingenuity, were bound by their own structure. Its military, scientists, and engineers worked in silos, developing isolated prototypes without the synergy needed to turn ideas into effective large-scale solutions. The United States' approach, on the other hand, was much more inclusive and open, allowing the brightest minds to work together to maximize output and efficiency. Rather than fragmenting efforts, the American system integrated science, industry, and government, creating a model of innovation that was more than technical. It was cultural. This model, more than any weapon or device, was what really made the difference. The American victory in World War II was not just a military victory, but a victory of freedom over oppression. The freedom to think, to question, to innovate was the real key to success. The story of the proximity fuse is a metaphor for this contrast. The modern world, in which cutting-edge technology and the most radical innovations are created in an environment of freedom and collaboration, rather than repression and fragmentation. What the United States did, unlike Germany, was to allow its citizens, its engineers, its scientists, its factories, to work together to achieve the impossible. This, then, is what we must learn from this story. The creation of the proximity fuse was not an isolated event, but part of a chain of events that demonstrated the superiority of a system based on freedom and collaboration. As we look to the future, we see that the nations that continue to thrive in technological innovation are those that maintain and cultivate the values of intellectual freedom and open collaboration. The proximity fuse, with all its military and technological implications, reminds us that a nation's greatest power lies not in its weapons or armies, but in the freedom and ability of its citizens to think freely and work together to solve the most complex problems. The proximity fuse was not only a tool of war, it was a symbol of the victory of the democratic model over totalitarian repression. The real lesson of this story is that innovation does not come from a regime that limits, but from a society that liberates, that integrates, that trusts. The smart weapons of the future, the technological devices that will shape the next century, will follow the same principle that began with that little fuse in 1943. The idea that collaboration and freedom of thought are the greatest weapons a nation can have. By the end of the war, Germany was broken, not only physically but ideologically, defeated not only by the bombings, but by its own inability to comprehend change. The thesis we have explored throughout this documentary is clear. The industrial power of the United States, combined with technological innovation and the strength of collaboration between science, industry, and democracy, was what guaranteed the victory. The proximity fuse, despite being a small and even apparently simple weapon, was decisive in changing the course of the conflicts. Not only did he change the dynamics of combat, but he collapsed the old military tactics. Precision, the capacity for mass production, and the integration of multiple sectors of American society were the ultimate collapse of Germany, which was trapped in fragmentation, totalitarianism, and a lack of adaptation to the new realities of modern warfare. Germany, by underestimating the capacity of her enemies and believing that her old doctrines could still prevail, sealed her fate. The great lesson that remains from this story does not only concern a war fought in the past, but about how logistics and the ability to adapt are the greatest determinants of a victorious strategy. When we talk about war, we often focus on tactics or brute military force, but the reality is that logistics determines strategy. It is mass production, the ability to adapt quickly to new conditions, real-time logistics that make the difference between success and failure. The victory of the United States, based on the power of an agile industry, is a lesson that reverberates in all areas of modern life, whether in the global economy, in trade, or even in social and political issues. As German General von Kluge declared after the defeat in the Ardennes, "We were defeated by trucks." This sentence perfectly encapsulates the irony of the story. It was not brilliant tactics or a superior military offensive that defeated Germany, but the ability to mobilize and apply resources in a coordinated and effective way, with impressive logistics that the Germans could not replicate. They were fighting against a future they couldn't understand, and so they lost the war. If you were impressed by the numbers and events we show here, like and subscribe to the channel to support the research and search for historical truth. Leave in the comments what was the most shocking fact you discovered in this video, and activate the bell so you don't miss the next devastating historical fact. Don't go away yet. Listen to the next true story that will appear on the screen. Always remember, logistics determines strategy. Watch the next video here on the channel with another incredible story.